Alright, hello class. In this video we are going to continue talking about the basics of vectors. And really, this is just to finalize a couple of things. For the first thing, everything we learned about vectors in 2 dimensions still works in 3 dimensions. Mathematically, it's all pretty much the same. The tricky part about it, though, becomes the visualization, right, and the graphing. So we'll talk about that. And there are a couple other things just to wrap up here before we start really complicating this like any good mathematician would. And yeah, let's just get started. All right, so 3D vectors, like I said, work pretty much the same way. We're going to have how much they move in the x direction, how much they move in the y direction, and how much they move in the vertical z direction. So then it just becomes a question of, well, how do we graph or talk about a 3-dimensional object on a 2-dimensional surface? And that's always the big problem or the big challenge or the big complication that we'll face in this class. And in fact, most of this class is actually about dealing with that issue, is representation of 3D object, okay, on a 2D surface, because pretty much all the surfaces we have to communicate our ideas in class especially, but even if you're watching this on a computer screen or your phone, that's a flat surface, right? Now, objects we can build in our real world, you know, we don't have that problem because we can move it around and look at it at different angles, but the big issue is trying to use our paper or our computer screens in ways that can help us visualize 3-dimensional objects. Okay, so this sort of standard way that the book likes to do it is they will make the vertical axis, I think they make it y, and then they make the 45-degree axis x, and then they make the vertical axis, z. Okay, so that the xy plane is here and z is pointing up out of it. Another way we can think about it, and I do it this way a lot, is to think of the xy plane like we normally would. And then I think about z actually pointing out towards us, right? So pointing out away from the screen. It's actually fairly tough to draw. But if you just think of it, what I will often do sometimes is on your wall, if you think about your wall as being the xy plane, and you put a pencil against the wall, so if you look at it from above, right, and you put your pencil against the wall, so it's a eraser against the wall, the direction the pencil is actually pointing in, I think of that as the positive z-axis, and if I were to point the pencil into the wall, that would be the, like into the wall, that would be the negative z. So this would be z negative, and this would be z positive, okay? But here's the truth of it all. It doesn't really matter. In fact, it's actually kind of funny. The book will say, oh, this here is the standard way we do things, and then they change it up all the time. Really, and you'll see me do this too, sometimes we will just draw things and set up our axes in the way that we can visualize the object in the best way. All right, so here I have a graph, and just from the way it looks, it's hard to tell what the x and y axis are, but we see here that the z is pointing straight up, and we can move things around. This is the xy plane here in gray. All right, and we can actually just sort of move things around however we want. Okay, so if I were to make a point, let me go ahead and do. Okay, so here's a point that I plotted here. This is the point 3, 4, 5. Let me see if I can put that on. All right, there we go. Here's point P, which is 3, 4, 5. And it's kind of, tricky to see how this works. But if I put a couple of lines that will sort of show how we get there, okay? Hopefully it'll be a little easier to visualize. So 3 means we go out 3 in the x-axis, okay? And so we'll go 3 in the x-axis and 4 along the y-axis. So I cleaned up the plane here a little bit. So now here in orange, I put the point 3, 4, 0. So we would go 3 along the x-axis. So there is positive 3 along the x-axis. So maybe I should move it around here. Okay. Then we will go 4 along the y-axis. Okay, so there we go. So we go 3 along the x-axis, x-axis, 4 along the y-axis. I tried to match the colors with the axes. Right, and then we are going to go up vertically by 5 units in the z-axis. All right, so we'll jump up. All right, so 3 in the x, 4 in the y, 5 in the z. So for me, with these little arrows, it's a little easier to visualize what's going on. Okay, so that is typically how we do points in 3 space, and vectors are defined in the same way as we do, like I said, in 2 dimensions. So if I made the vector 3, 4, 5, it would look like this. Okay, so here's the vector, let's say v, which is the vector 3, 4, 5. Okay, there we go. Fix the labeling there, but as we can see, it's the vector that goes from the origin to the point 3, 4, 5. So it begins at the origin and terminates at the point 3, 4, 5. Okay, so let's get these out of the way. Okay, so this is really how vectors operate in 3 dimensions, and we can basically deal with them in the same way that we do or as we did in the past. So for example, we could add and subtract them, and it still operates in the same way. So let me throw down another vector and show you the resultant. All right, here's another vector I have. So here's v, which is 3, 4, 5, and here's w, which is 2, -3, -2. And I brought the plane back and got rid of the grid. And the reason I did that is because this software does a pretty nice job of when it's in the negative z's, or if it's behind this plane, it will be like a dotted line here. So this guy we see is going in the positive z's, while this one goes down to the negative z's. So if I flatten this out, right, where I make it level, so we're looking straight on to the xy plane, we see that W is pointing in, like down into the negative z's, while V is pointing up into the positive z's. So when I bring it up, now I'm looking above. So we can think of this as the floor. Imagine that this is the floor. This vector is pointing up towards the ceiling. This one's pointing into the floor. So now we can think of this as, now we're below the floor, looking up. Now this vector that's pointing down is pointing at us, while this one is up above us here. Okay? So, here's our two vectors, v and w. Now I'm going to add them together, and we still do it component-wise, okay? Just like we would expect. So we should get 5, 1, 3. All right, now here's the resultant vector, v plus w, 5, 1, 3. And it might be harder to see in 3 dimensions like this, but it is the combination of these two forces acting on the origin, and it does make a parallelogram. It's just in 3 dimensions, so it's a little more difficult to visualize, but hopefully with this software doing it for us, it's a lot nicer than it would be otherwise. All right, so so mathematically it all works out the same, and it turns out that the magnitude is calculated exactly the same way. Okay, so if we have a 3-dimensional vector here, say v, which is x, y, z, okay, then the magnitude is the same as, or follows the same pattern as we had before, that the magnitude of v is the square root of x squared plus y squared plus z squared. Okay, well, why would that be? Why is it the same exact formula? Shouldn't it be a little more complicated than that? It turns out, no, not at all. All right, so let's suppose we have a vector on the x, y, z, not plane, but axes here. So let's suppose here's my vector v. Okay, and it terminates at the point x, y, z. In other words, it is the vector x, y, z. Okay, so its magnitude is going to be the length of this line. Well, if we project this point straight down to the xy plane, wherever it might hit the xy plane, right here is the point x, y, 0. Okay, so that corresponds to the distance of x on the, of course, x axis. And I'm going to try and match the colors we had on the software. And so this would be y. Okay? And this vector itself makes a shadow on the xy plane. Right? It makes a shadow. And specifically, its shadow is this vector here. We'll call it w. And that's the vector x, y, 0. And the length of this shadow that it's making on the xy plane, so if you imagine a light here, shining downwards, straight downwards, it's making a shadow vector, which some would call a orthogonal projection, right? I don't want to get too deep into the woods there, but its length is going to be the magnitude of this vector. And from what we established before, this magnitude is the square root of x squared plus y squared. Okay? So I'm going to call this length r, just to simplify it a little bit. Okay, but maybe you've noticed now that we've actually created a right triangle. It's just kind of slanted, right? It's jutting out diagonally across the xy plane, but we've actually created a right triangle here. Okay, where one side is going to be the magnitude of our vector that we're looking for. This side is r, the base is r, and this length here, well, that's just z. That's how far we go in the z-axis. Okay, and so now, by the Pythagorean theorem, we will have that the magnitude of v squared is equal to r squared plus z squared. Oh, well, r squared, this was r, so r squared is this thing squared, which is a square root. So that's going to be the square root of x squared plus y squared, all squared, plus z squared. So the whole thing comes out to be x squared plus y squared plus z squared. And then when we take the square root, this tells us that the magnitude of v is the square root of x squared plus y squared plus z squared. And it turns out that we can continue this process, because remember we talked about in the last video that the absolute value, so a one-dimensional vector is just the square root of x squared, two-dimensional x squared plus y squared, three-dimensional, we add in a z squared. If we wanted to go to 4 dimensions, we could. We would just add in another, and so on and so forth. And that's just how this works. We just continue applying the Pythagorean theorem. Okay, so the magnitudes are also done the same way, right? Scalar multiplication is done the same way in 3 dimensions. It just is scaling in 3D. Okay, so everything we've learned so far in 2 dimensions is pretty much going to work the same as it does in 3 dimensions. It's just the visualization that gets a little more complicated. All right, the last thing to talk about here is unit vectors. Okay, so unit vectors are basically just vectors with magnitude equal to 1. So these are vectors with magnitude equal to 1. Okay, and these serve a really important purpose, because what unit vectors basically do is reduce the idea of a vector down to just its direction. Okay, now we'll get into later why that's important, but if there's any sort of formula where you need just the direction from a vector, you're going to want to use a unit vector so that the magnitude of that vector doesn't alter your final answer in what you're doing. Okay, so like I said, it'll be easier to grasp what I'm talking about when we get to that a little later, but in the next, I think it's the next section, we'll actually see our first example of that. But basically it helps us just have the direction so we don't have to deal with the magnitude, because if the magnitude is 1, as we multiply it or divide it or do all those any of those little things we want to do, that 1 is not going to alter anything. Okay, so given a vector v, okay, let me say it this way, the unit vectors parallel to v are, well, I'll take v and divide by its magnitude. That's pretty much it. And negative v divided by its magnitude, right? So any vector will have 2 unit vectors parallel to it, one in the same direction, one in the exact opposite direction. Okay, so to give an example of how this works, suppose v is something really simple like 1, 1. Okay, the unit vectors are parallel to v are, well, they're going to be plus or minus v over the magnitude of v. So first we need to calculate the magnitude of v. Okay, so let's give ourselves a new line here and do that. The magnitude of v is of course going to be the square root of 1 squared plus 1 squared, which is going to be the square root of 2. Now I'm just going to leave that like that for now, because our unit vectors, and I'll do u1, will be v divided by this magnitude. Okay, so that's going to be our vector, which is 1, 1, and we're dividing it by the square root of 2. Well, this is just technically scalar multiplication, because this is technically 1 over root 2 times 1 comma 1, which will be 1 over root 2 comma 1 over root 2. Now, at the moment, this might not remind us of anything, okay? But if we rationalize the denominator, again, we don't have to do this. I'm just trying to show a pattern here. If we multiply the top and the bottom by root 2, we get this vector here, square root of 2 over 2, comma, square root of 2 over 2. Now, hopefully, this looks familiar. This should remind us of sine and cosine of 45 degrees, or pi over 4. All right, this is cosine of pi over 4. This is sine of pi over 4. And that's exactly what we should have gotten, because the vector 1, 1, if I put that on the xy plane, okay, the vector 1, 1 should make a 45-degree angle, and it does. That the point 1, 1, 2, 2, 3, 3, that corresponds with a 45-degree angle. And if we reduce the length down to 1 to get our unit vector, it's going to just put it on the unit circle. So in a lot of cases, these unit vectors should correspond with the cosine and sines that we know if they're known angles. Okay, and then the other one, once you find one of them, the second one is just going to be the negative. Right, that's the one that just goes in the opposite direction. Okay, but okay, so that's unit vectors. The importance of them will hopefully become a little more clear as we go further. What I want to do as the last part of this particular video is talk about some of our important unit vectors. Okay, so the important unit vectors, the big ones that we use a lot, have their own names. We have I, J, and K. And you'll notice that I don't put the dots over I and J. I just use the arrow instead. Now don't confuse this with the complex number I. Okay, this vector I is the vector 1, 0, 0. The vector J is the vector 0, 1, 0. And the vector K is 0, 0, 1. These are important because these are the vectors that represent each axis. They represent the x, y, and z axes. All right, so given the x, y, z axes, I is the vector that corresponds with the x-axis. J is the vector that corresponds with the y-axis. And k, of course, is the vector that corresponds with the z-axis, and specifically the positive axes in all of these. Okay? And where these come into play is the fact that every vector can be represented in terms of these three. Okay, so how is that? Well, it turns out that if I have the vector, let's say, 2, -7, 1, let's say, this can be written as instead 2i minus 7j plus k, which, note, we have a 1 sitting out there. Okay, so all vectors can be represented in terms of I, j, and k. Let me make sure I have an arrow there, instead of in bracket notation. Now, you might wonder why in the world we would ever want to do that, and are we sure about that? Well, let me show you why it works. 2i, well, that's going to be a scalar multiplication, so 2, and that'll be times I, which is 1, 0, 0. And we have minus 7 times j, which is 0, 1, 0. And we'll have plus k, and that's just 0, 0, 1. Okay, so now we'll do our scalar multiplications. A couple ways we could do this. I'm going to do it like this. This will be the vector 2, 0, 0, plus the vector 0, -7, 0, plus the vector 0, 0, 1. And now when we add these, we just combine all the components, component-wise, and since there are zeros in pretty much most of these, we'll just get the vector 2, -7, 1. Okay, so this is great. Your question might be why we would ever do this. And it really just comes down to what it is that we're working with. Bracket notation can get really messy if, say, we have something really awful in one of our components, like we have e to the 2 pi plus pi over 3 all over the natural log of 7 plus, let's do another pi, plus the cosine of 3. Okay, and let's just say that's our first component. Notice how big our brackets have to be and just how cluttered it can be, versus I could just do, it might not look much better, but we could do e to the 2 pi plus pi over 3 all over ln of 7 plus pi plus cosine 3. But what we can do instead is just throw an I in here and then do plus whatever the next component is. And when you're doing a lot of algebraic manipulations, believe it or not, this format comes out to be a little nicer because this I, j, and k works just like variables. Okay, they work like variables. So it can make doing algebra with a lot of vectors a lot nicer looking than trying to put brackets and stuff in them. Okay, so that's really the big deal. Usually MyLabs, if you're doing your homework, will tell you what format it wants it to be in. Okay, I typically, for me, I don't care that much. As long as it's written correctly, I can read it, So this notation just turns vectors into, as written, algebraic objects, okay, as sums. Okay, and so that can, in some cases, make them easier to deal with, and we'll be using these vectors quite a lot. They show up in quite a lot of places. And I think that should be it as far as our super basic vectors. In the next sections, we'll be looking at the other multiplications, because as we talked about last time, is there vector multiplication? The answer is sort of. And we're going to talk about in the next sections what that sort of means and why it's only sort of. All right? So, I will catch you all on that next lecture video. And until then, cheers.